Okay, yeah. Thanks everyone for coming. This is a recent work that I have done with Vincent and two people from RPI in New York. This is Professor Ali and his student Arpan. This work came about when Ali visited NUS in January, and we got to discussing this problem. And yeah, I'm eager to share this with you. So I'll start with fixed confidence BAI. I'm sure most of you already know the setup. I just want to quickly go through some basics and highlight a few things that I will be using towards the second half of the talk. Okay, so fixed confidence BAI. So let's say there are 4 arms, and then the means are mu1, mu2, mu3, and mu4. There is one unique best arm, which is the one which has the highest mean. And the learner, you as a learner, can only select one arm at a time. So let's say time starts from 0, and arm 1 is chosen at time 0, arm 2 at time 1, and so on. So this goes on up to some time. At any given time, the arm that is selected can potentially depend on all the previous arms and the previous observations that were seen. X bar is the observation. This potentially goes on up to some time, some random tau, at which time you decide to stop, and you declare a guess. You output a guess of the best arm. Now, in this fixed confidence regime, the interest is, given a certain delta, which is called the confidence level, you would like to design such an algorithm for identifying the best arm, which stops in finite time and outputs the correct answer with probability 1 minus delta, at least 1 minus delta. This is what is of interest. Now, of course, at each time instant, as I said, the arm that is selected can potentially depend on all the previous observations and the arms. So we'll try to make this a little more formal. So let's say pi n is a rule for choosing arm an at time n, if at all we decide to choose arm an. Otherwise, we stop. So it's a rule which says we have to either stop at any given time or you continue. If you're continuing, how will you choose an? Potentially based on all the previous, the history. So let's say this is what I call as a policy pi. I denote a policy as pi. So let's say tau pi is its stopping time, and then a pi is the guess. Whatever I showed on the previous slide is just this. Our interest is in designing algorithms or policies which satisfy this criterion. We are given delta. Delta is something which is given to us. We would like to design policies in this class, which is the class of all policies which stop in finite time with probability 1 and output the correct answer with probability at least 1 minus delta. That's all, as simple as that. Now, in the fixed confidence, this is what is called a fixed confidence best arm identification problem. Fixed confidence because delta is fixed and given to us. Now, in this class, in such fixed confidence problems, what is of interest is, okay, you stop in finite time with probability 1, but what can you say about the expected value of that stopping time? So how does that expected stopping time grow as a function of delta? This is what is of interest generally. Given a mu, meaning the mu1, mu2, mu3, mu4, that is fixed. For any given mu, you want to ask this question as to how does that quantity grow? So there may be many policies which satisfy this particular criterion, that is both these criteria. Among all those policies, which is the quickest one? That is the infimum of expected stopping time. So in that class, you would like to find the quickest or the shortest time that is required to find the best arm, given the delta, and you would like to then find at what rate does that quickest time, that shortest time, grow as delta goes to 0. So this is what is of interest. Now there is this classical result by Garivier and Kaufman from 2016, which says, okay, sorry, I missed log 1 over delta here. So essentially it says that this particular quantity, that is infimum over pi in pi delta of this quantity, grows as logarithm of 1 by delta. And if you look at the expected value of stopping time divided by log 1 by delta, I'm sorry, I missed that log 1 by delta there in the slide. And if you look at the infimum over all pi in pi delta, and you look at limit as delta goes to 0, this is lower bounded by 1 by t star of mu, where mu is something which is given, that is this vector of R means. So this is an instance dependent lower bound on the expected stopping time. There is a divided by log 1 over delta here. So this t star mu arises as the solution to a game between the learner who is trying to learn the best term versus the environment which is trying to confuse the learner. So by confusing, I mean the environment wants to delay the identification of the best term as much as possible, and the learner wants to identify the best term as quickly as possible. So there is a conflicting behavior there. So this T star mu is also very well known. Okay, so the way we interpret T star is the environment. So this is the amount of information that the learner can collect when choosing the arms according to a certain distribution nu. Nu is a distribution on the arms. Whenever the learner plays according to this distribution, the learner collects this much amount of information. And here the environment is trying to confuse the learner. The true instance is mu. In mu, there is a best term which the learner wants to identify. The environment tries to confuse the learner into believing that the true instance is not mu, but some other lambda. An alternative lambda. What is alternative lambda? It's the collection of, alt mu. Alt mu is the collection of all lambdas in which the best term is different from the best term in mu. So there is a best term corresponding to mu. That is what the learner wants to identify. Alt mu is the collection of all instances for which the best term is different from the true best term. If the learner identifies any one of these as the best term, he is wrong. So these are all the confusing instances, so to say, which trick the learner into believing that the best term is something else other than A star mu. Now the learner wants to avoid identifying anything in this set. So this is the amount of confusion that the environment creates, the infimum. Among all the confusers, the most confusing instance has to be kept as far away as possible by the learner. That's the idea of this soup inf. Okay, this is just the usual game theoretic interpretation. I won't go into too much of detail, but the point I want to make here is there is a very well known algorithm which will achieve this. Okay. By the way, in the first slide when I showed you all the observations, I was assuming that all the observations are independent of each other. Okay, from each arm the successive observations are all independent. Now there is a very well known algorithm which will do this. That algorithm can be broken down at a high level into 3 parts. First part is estimate the unknown. You don't know the mu vector, estimate that vector using the observations. Importantly, if you look at the inner infimum term, okay, that is what I called as the psi on the previous slide. Just look at the inner infimum term. That's a function of mu for any given mu and then the instance mu. Okay. If you only look at that, if you plug in mu hat of n instead of mu, okay, that's what the learner will try to do. The learner will try to find the maximum, the optimum distribution, assuming that mu hat n itself is the true instance. The learner doesn't know the true instance. The learner will assume that mu hat n is the true instance and try to find what is the optimum distribution for this mu hat n, according to which the learner should sample the next arm. And the next arm that is sampled by the learner is actually according to this. Okay, this mixture is just to take care of the fact that every arm is selected with a strictly positive probability. So this mu star n, it may not always be the case that this mu star n puts a strictly positive probability on all the arms. Just to make sure that that happens, the learner can possibly mix it with a uniform distribution on the arms. Okay, so with a small probability, you pick an arm uniformly at random. The learner will pick an arm uniformly at random. Otherwise, the learner is going to pick an arm according to this mu star mu hat n. By doing this, the learner, along with this rule, actually, I think I may have skipped one slide. Yeah, sorry about that. So these are the 3 aspects. Now, can that lower bound that I showed on the previous slide, can that be achieved is the question. In order to achieve that lower bound, there are 3 key ideas. So once these are done, the learner will keep doing these at every time step. So as long as this is done, you just have to make sure that mu hat n converges to the correct mu as n goes to infinity. This is the optimum distribution corresponding to mu hat n. If you can guarantee that that will converge to the optimum distribution under the true instance mu, and if you can guarantee that the empirical proportion of times each arm is selected converges to the proportion that is actually given by the lower bound. Mu star is the optimum corresponding to the lower bound. Okay. Mu star is the one which attains the supremum in that expression for T star mu. As long as you can guarantee that the empirical fraction of arm pulls converges to that optimum proportion, these three will help you guarantee that you can get an upper bound like this. The eta comes from the eta mixture. It's a very small thing, you can neglect that eta. So this is the whatever I described here is the arm selection rule. That is how you select the arms. There is also a component on when you will decide to stop. How, at what time will you stop? How will you decide when to stop? That is based on a certain generalized likelihood ratio test statistic. A generalized likelihood ratio test combined with an appropriate threshold. So you measure the value of the statistic. You keep computing this statistic at each time instant. Also, you keep updating a certain threshold. Both of these will keep getting updated at each time instant along with all of these. The moment this statistic exceeds the threshold, you stop and you declare whatever is your estimated best arm as the true best arm. You just declare that as the best arm and come out. That's all. So that particular policy will actually satisfy your desired error probability. Whatever delta you give, it will satisfy the delta error probability because the threshold that you will be comparing against will be a function of delta. It will be adjusted accordingly so that you get delta error probability. So with this, you can get this type of a bound. Okay. So all this works for IID observations. Okay. My talk is not about IID observations. This is Garibia-Kaufman. Now, the important thing is in some problems, the distributions that these arms follow is assumed to be a parametric family. Okay. That is, each of these distributions can be parameterized by a certain parameter, a scalar or a vector parameter. For example, the single parameter exponential family is a very well-known class of parametric distributions. The Gaussian, Bernoulli, binomial, exponential, Poisson, all of those fall into that single parameter exponential family. Okay. All on the previous, until now, I only told you about the means. I never told you about the actual distribution. But it turns out that in the analysis, that is in the literature, people have explored such parametric distributions also. In such parametric distributions, it is the parameters which completely determine the problem instance. Given the parameters, you know the distributions, you know their means also. So whatever I wrote as T star of mu on the previous slide can now be written as T star of theta in this case. When we look at parametric models, exact same thing. Now, when we look at lambda belonging to alt theta, you should interpret it accordingly. Okay. Earlier it was set of means, here it's a set of parameters. That's all. The most important thing is that in such problems, where such exponential families are considered, there is a one-to-one correspondence between the parameter which parameterizes the distribution and the mean of the distribution. What that means is the learner can estimate the mean from the observations and get back to the parameter. Okay, you may ask me, why is that important? Why do you have to get back to the parameter? Why can't you just simply estimate the mean and declare? Because for declaring the best arm, you only need the mean. You don't need the value of the parameter, right? Why is it important to go back to the parameter? Is a very important question that you may have. That is because if you look at the lower bound, if you look at this particular thing carefully, the learner has to estimate this optimum distribution corresponding to the estimated parameter. If mu hat n is the estimated mean, the lower bound is not governed by the means, but it is governed by the parameters. So there is a T star of theta. In the case when it is theta, it is T star of theta. So there is an optimum nu theta star. The learner should be able to estimate the parameter theta hat n at any given time. So the theta and the mu are always in one-to-one correspondence in exponential families. Okay. So here the learner was able to estimate mu hat n and then derive the optimum distribution corresponding to mu hat n. In the parametric version, the learner will first estimate mu hat n. invert to theta hat n and estimate the optimum distribution corresponding to theta hat n. The optimum distribution is a function of the parameters, not directly of the means.
So are there other families that are invertible like this?
Exponential family is the most widely used, the canonical exponential families. I don't know of any other. Otherwise, they will explicitly state that we consider sub-Gaussian arms whose distributions are parameterized by the means.
Okay.
Mean is the only unknown.
I see.
Something like that.
And the exponential family have more than one parameter?
Yes, yes. There are vector parameter exponential families also.
Which is also, your result also covers that. So,
Yes. So the important thing is to be able to go back between them, to go back and forth between the parameters and the means in such models. Okay.
So it's not always obvious that all distributions can do this, right? This
No,
capability.
no.
It's specific to exponential.
Yes. Exponential is one I know.
Oh.
There may be others. Exponential is one very clearly understood model in statistics where such a back and forth invertibility is available.
Oh.
Okay, so this is the important thing I want you to take away from this first part, which is the optimum distribution depends on the underlying instance, whatever that means. If the underlying instance is in terms of parameters, it depends on the parameter. If the underlying instance is in terms of the means, it is in the distribution depends on the means. Okay, so we want to have this kind of a flexibility. Okay, and what I'm now going to describe over the next maybe 40 minutes or so is how do we extend all of this best term identification setup, that framework, when each arm gives Markov observations instead of IID observations. So here until now everything was IID, that is this whole process was IID. What if this is a Markov chain? What can you do then? Is the question. So that's what I'm going to be talking about. Okay. So in particular, I'm going to consider what is called a restless Markovian setting. That means, let's say the learner has picked all of this. Importantly, at time 1, at time n equal to 1, the learner can observe x12. The learner cannot observe x02. At time 2, the learner picks arm 3, gets to observe x23, but has lost information about x13 and x03. They are not available to the learner anymore. The system has already evolved. So even though a particular arm is not selected, that arm continues to evolve. Now this continued evolution did not matter in the IID case because all these observations are independent of this observation. But in the Markovian setting, they will matter. Okay. So at time 3, the learner, let's say, picks arm 4. The learner observes x34 directly. The system has already evolved 4 time steps from time 0 to time 3. So that is the important difference, and that will matter a lot. You will see how much more complicated this problem is because of this.
how we define the best term?
I'll now come to that. Yeah, I'll come to that. So we impose some regularity conditions to make this problem well defined. First, we assume that the state space of all the arms is the same. This is like saying that we have 4 coins. The coins are Markovian. You want to identify the best coin. All the coins have the same 2 faces, heads and tails. That's all I want to say. It's a common finite state space. Just by observing the state, you cannot tell which arm it is. Okay. And then we assume that the instance, whatever I have denoted as mu1, mu2, mu3, mu4 in the IID case, here it is given by transition probability matrix P1, P2, P3, P4. So each arm has its own transition probability matrix. It's a finite dimensional matrix, square matrix. If there are S states in the state space, it's a S cross S matrix. Each of those matrices is an S cross S matrix.
So the arms are still independent.
Arms are still independent of each other. We assume that each of these transition matrices is ergodic. Ergodic just means irreducible, aperiodic, and positive recurrent. If it because this is a finite state Markov chain, irreducible and irreducible and positive recurrent will just mean that there exists a stationary distribution. But whatever it is, we assume that each of this is an ergodic matrix. Because it is ergodic, each matrix will be associated with a stationary distribution. Call mu A as the stationary distribution of PA. The P1, P2, P3, P4 are not known. Therefore, mu1, mu2, mu3, mu4 are not known. Okay. Now, the question is, like Rajab asked, how do we define the mean of any given arm? And once we define, how do we ensure that there is a one-to-one correspondence between the mean and the matrix? Because remember, we will need to go back to the matrix. Like how we felt the need to go back to theta in the IID case, we will find the need to go back to P from the mean. All we can estimate is the mean. We will need to go back to the matrix also. So how do we define the mean and how do we ensure that such a one-to-one correspondence between the mean and the TPM exists? So this is where I will introduce what is called a single parameter exponential family for Markov chains. Single parameter exponential family for IID observations is very well known and understood. This is not so well explored, although this has been studied very well from an information geometric viewpoint also. Okay, so what is the model? This is a single parameter exponential family to generate matrices. Let's see how that can be done. We start with a parameter space theta. I am now assuming that the parameter space is a scalar space. We can easily extend it to vector parameters. We start with a generator matrix P, which we assume is irreducible. And we are given the reward function f. Let's say this is a function of the state space of the arms. S is the state space of the arms. So these three are required to generate our model, to describe our model. So the model is as follows. Given any theta, you first, so given the theta, given any particular theta in that space theta and the generator, you do an exponential tilt of the generator to get this matrix P tilde theta. What is P tilde theta? It is a tilt of the matrix P. It is an exponential tilt of the matrix P.
So
Yeah.
yeah. So P is common across all the arms, is it?
Yes.
Yeah, I was going to ask this.
P and F are common across all the arms. These will define the model. I have not yet come to the arms. I am just describing how to generate a matrix from how to generate a parametric family of matrices.
The only thing that differs from arm to arm is
Theta, correct, yes. So this whole model will be defined as a P comma F model. Okay. So do an exponential tilt. Now, once you do an exponential tilt, this matrix may not be a stochastic matrix. That is, its rows may not sum up to 1. So you appropriately normalize it using some Perron-Frobenius theory, and you arrive at this P theta. Okay, I won't describe the exact form. That is not what is important. The point is, by doing this kind of a transformation, what properties can you guarantee about this P theta for any theta? Number one, P theta is ergodic for every theta. Its stationary distribution also has a certain closed form expression which comes from the Perron left and right eigenvectors. The second most important thing is if you define the mean of the matrix P theta as the average value of that function f appearing here. If you define the mean value of P theta, this matrix P theta, as the average value of f under the stationary distribution of P theta, which is mu theta. Stationary distribution of P theta is mu theta. If you define the mean of f, the mean of P theta as the average value of f with respect to mu theta, it turns out that theta to the mean, theta to its mean is a bijection.
So the only assumption on P is irreducibility.
Irreducibility. Yes.
No need of ergodic.
No. Okay, so this kind of a model. So we were all wondering, given a matrix, how do we define its mean? So we have a matrix, we have some function. That function will generate a model. Okay, along with theta. For that model, you define the mean of that matrix as this. The f has to be the same. Okay, the f is the one which is generating the model. You have to look at the average value of f under mu theta. If you define the mean of that matrix like this, then any theta to its mean, that mapping is a bijection. In particular, it is a one-to-one mapping. So there is a one-to-one correspondence between the mean and the theta. We will use this model now because we will be able to estimate the mean of any particular arm and we will be able to go back to its theta using this particular model.
What is mu theta here?
Mu theta is the stationary distribution associated with P theta.
Okay.
It has a certain closed form expression. It's just the entry-wise product of U theta and V theta. U theta and V theta are vectors.
Okay.
U theta is a certain left eigenvector and V theta is a certain right eigenvector of this P tilde matrix. Both of them are equal length vectors. Take the corresponding entry-wise product, you will get another vector. That vector is mu theta.
I see. Is that why you gave the tilt interpretation? Because these are the eigenvectors? Because they are being rotated twice.
That's correct. Yes.
Okay.
Yes.
So is it even for that between F and mu theta, is it the mean of this stationary distribution or are we different?
So the stationary distribution is a vector.
Yeah, because we can.
You weigh it with f of I. You weigh the mass on state I with f of I.
I see.
And then you subtract.
F is a known.
It's a known function. P and F is given to us. The model is known to us.
Okay.
We know the model from which the arm TPMs are coming.
I see.
Yeah. Okay, so I mean, I thought this is a nice thing. So for single parameter exponential families, we have a one-to-one correspondence between the parameter and the mean. Likewise, there is a correspondence between the parameter and its mean in matrix in single parameter exponential family for Markov chains. And this is the model. So now I'm going to impose this model in the problem. Restless Markov arms. The transition matrices of the arms are parameterized by parameters theta 1, theta 2, theta 3, theta 4, following that single parameter exponential family model that I just described. Okay. So in the analysis, so that was the model. So we'll begin the analysis. Okay. Now is where the interesting part starts. Okay. So in the analysis, we will see that there is a Markov decision process which will come in. Okay. That's the beauty of this Markovian system. And which is what makes the whole problem a lot more difficult than the IID setting. So what's the Markov decision process? Let's say the learner, you as a learner have selected the arms and you have gotten some observations up to some time, let's say time 7. Now you are yet to select an arm at time 8. At this time, I'm going to show you two tables here. Okay. One is what I call the table of arm delays. By a delay, I mean how many time instants ago was each of the arms selected with reference to a certain time. For example, with reference to time n equal to 8, how many time instants ago was arm 1 observed? How many time instants ago was it observed? It was observed one time instant ago at time 7. That is why the delay is equal to 1 at time n equal to 8. How many time instants ago was arm 2 observed? Arm 2 was observed previously at time 6. After that, it was not observed at all. So the delay is 2. Arm 3 was observed last at time 5. It was not observed after that. So there is a delay of 3. So likewise, you can compute the delays. While you compute the delays, you can also note down what were the previously observed states. At those previously, at those delays, what were the previously observed states? That was x71 for arm 1, x62, x53, and x34. In relation to time n equal to 8. We'll just do this exercise for a couple more time instants and you'll know what's happening. So let's say we evolve by one time step. Let's say arm 2 was chosen at time 8 for some reason. Now all of these will get updated. Correct? Now can you tell me what is the value of this? How many time instants ago was arm 1 observed? 2 time instants ago. So this will increment. What about this? Now that will change to 1 because you observed arm 2 in the previous time instant, n equal to 8. All the unobserved ones will just keep incrementing. Here, unobserved ones will remain changed. Whatever was observed will get updated. That's all. So you can just build this table. Okay? You can keep building this table for all times. If you collect any particular, focus on any particular time n, collect the vector of this particular row of this table and the corresponding row of the below table. One vector I'm going to call as vector dn, that is the vector of all arm delays. Another vector I'm going to call vector in, which is the vector of all last observed states. For each n, you can construct these vectors. Okay? Now you can see that based on D and IN, there was a certain arm which was chosen. D and IN got updated. Another arm AN plus 1 was chosen. Again DN plus 1, IN plus 1 got updated, and so on. So you see that DN IN somehow captures the entire summary of the system. So that can be viewed as a state. It's like a sufficient statistic of the system.
So this is only possible because of the state space being the same.
Same, yes. Okay, so DNIN in some sense represents the state of the system at time n, following which there was an action which was chosen, which is AN, the arm that was chosen. Then the state got updated, the next action followed, state got updated. So there's a state, action, which is naturally the MDP setting. Okay, so we have a Markov decision process, which is the process of all the DNIN. Its state space is the space of all such vectors, space of this kind of a vector and this kind of a vector. This is a countably infinite state space because each row here, the entries are all integers, right? The action space is the space of arms, which is finite. One can write down the transition probabilities of this MDP. Given a certain state and given an action, what is the probability of seeing the next state? There is a very deterministic way in which the D will evolve. The D will increment when an arm is not observed. Otherwise, the D will be set to 1 whenever an arm is observed. So based on that, you can write down a certain transition probability for this MDP. Okay. The important thing is it's not the expression, but the fact that there are powers of matrices which will come here. The power is a function of the delay. Okay. For example, if you were to look at what is the probability that the current state was 8, the current time instant, at the current time instant, the current state is D8, I8, action A8 was chosen, you go into some state D9, I9. What is the probability that this happens? Given that action A8 is equal to 2, that means arm 2 was chosen, that is in blue. It's the probability that you transition from x62, that was the previously observed one, to x82 after a gap of 2 time instants. So that is simply the transition matrix P theta 2 raised to the power 2. Correct? So that's what it is. It's a very simple calculation. If you were to do the same thing for the green arm 3, you will notice that there is a probability of transitioning from 5 to 9 with a gap of 4. So that 4 will come in this matrix in the expression for the transition probability. So the important thing is to note that there are powers here. Okay, so that's what will come. So this is the MDP. So this particular state action process has a natural implication, or it has something going on inside it trivially, which is just a very keen observation, which is anytime a particular state, let's say there was a DNIN, there was an action AN which was chosen, the system entered a state DN plus 1, IN plus 1, action AN plus 1 was chosen, the system enters a state DN plus 2, IN plus 2, and so on. Every time the system enters a certain state, it will leave that state and enter a new state. Then it will leave that state and enter a new state. For every DI, the number of entries and the number of exits will match.
There are no cycles.
There are no, I mean, it's not about cycle. It's just that this will happen every time except for the first state and the last state. The first time instant and the last time instant. In the first time instant, there will only be an exit. Last time instant, there will only be an entry. Last time instant, I mean the stopping time. Otherwise, for every intermediate state, there will every entry is matched by an exit. The system will enter a state and exit that state because a new action was chosen. So this is something that can be captured mathematically. Okay, so you can capture saying the number of times the system is in certain state D prime I prime. This is like the total number of times you have exited. This is like the total number of times you have entered. So this is some inequality which is always satisfied for every DI. Okay, so you can prove this. I'll tell you why this is important. Now, I told you that this whole Markov decision process is a countable state MDP. The countable state space is coming from the fact that the D values are all positive integer valued and they will keep growing if you don't select an arm. Okay. So it turns out that analyzing countable state MDPs is actually quite hard. Okay, you require some regularity conditions on the MDP, some assumptions that will make the problem amenable to analysis. Okay, and such assumptions are not very feasible in this setting because they will actually imply that we will be constraining the set of all policies of the learner. So, for example, one assumption which is very common in the literature on MDPs when dealing with countable state MDPs is under every stationary policy, the MDP is ergodic. Okay, the MDP is state action, state action, state action. Whenever the actions are chosen in a stationary fashion, that means independent of time, they are chosen in the same rule. Then the state process itself will become a Markov chain. Okay, so that Markov chain should be ergodic. That is one very common assumption in the literature. If you were to impose such an assumption here, it will mean that you are significantly constraining the class of all policies that you are allowing for the learner. So we did not want to do that. Instead, what we do in order to make this problem amenable to analysis, at this stage, as a countable state MDP, we cannot proceed further. It's very difficult to analyze the problem. So what we do is, we will introduce a constraint in the problem setting itself. We will say that whenever the delay of a certain arm exceeds a prescribed value R, we are going to forcefully pull that arm in the next time instant. Okay, the delay of an arm will increase whenever the arm is not selected. This means that you cannot leave an arm unselected for a very long time. If an arm is not observed for a very long time, you better go and observe it. That is what this constraint will say. Okay, so for example, this is a snapshot from the previous table I showed you. If, for example, we say that R is equal to 6, that means whenever one of these components becomes equal to 6, you have to select that in the next time instant. Earlier, that was not the case. You selected arm 10, you selected arm 3. See, at time 9, the fourth arm's delay has become equal to 6. Earlier, there was no R, so you were free to select arm 3. But now, because this has reached 6 and R is also equal to 6, you have to forcefully select this at the next time instant.
So you basically won't have 6 in the table.
You will have a 6, you won't have 7.
7 and 8.
Once it reaches 6, the next time instant, it will reset to 1. Okay, so this is what we are going to introduce. So along with this is the flow constraint that I described. Every entry into a state is matched by an exit. Entry is equal to exits is the first equation. Second equation is whenever delay equal to R, forcefully sample it. Okay, that's another way of saying that. Okay, so once we have these two, our objective is fixed confidence best arm identification under flow constraint and max delay constraint. So that delay constraint, whatever I showed, I call it as the R max delay constraint, where R is the parameter that is input into the algorithm and the system, the problem formulation itself. Okay, so we have K. So the summary is we have K Markov chains independent of each other. The Markov chains will evolve whether they are selected or not. So the arms are restless. The transition matrices of the arms are parameterized by parameters, and the model is that of a single parameter exponential family for Markov chains. There is a one-to-one correspondence between the parameter and its mean. We want to do best arm identification in the fixed confidence regime, assuming that there is a constraint on the allowable delay for each arm.
So, Karthik, can you hear me?
Yes, yes.
So this R max delay constraint is something we introduced to make the problem tractable, because countable state space MDPs are difficult to deal with analytically. Yeah,
correct. Yes.
So how restrictive is this assumption? Do you think?
So I will show a little bit of our analysis on what happens as R goes to infinity.
Okay.
Towards the end of the talk, I will show what happens as we let R go to infinity. But I mean, as such, this is just a reduction of the uncountable state space to the countable state space without much compromise on the actual results.
I see. Oh, okay. Without much compromise. Okay.
Yeah, so I'll come to that actually.
All right, sure.
Yeah.
But by the way, I need to leave at 5 o'clock. The recording will end at 5 o'clock. Unless, maybe there's another way to continue recording. All right. Let me figure out.
Okay. Yeah, I'll be quick. So there are two parts left. I just need to tell you what is the lower bound and how to achieve the lower bound. So the lower bound is very similar to the lower bound that we had on the. I'll directly go here. So the lower bound is very similar to the lower bound we had in the IID setting. Okay. This is 1 by TR star is the actual lower bound. Okay. TR star of theta is a problem dependent constant. Theta here is the vector of parameters, theta 1, theta 2, theta 3, theta 4, following that single parameter exponential family for Markov chains model. So that is this. So what is the TR star? How does that differ from the T star of mu that I showed in the IID setting? So in the IID setting, there was only mu of A. Now here there is a DIA. DI is the state of the MDP. A is the action. So these are all state action distributions. The supremum now is over state action distributions of the MDP. Okay, the learner will play a certain mu, and then the learner will accumulate some information. The agent is trying to confuse the learner. The learner wants to keep the most confusing instance as far away as possible. All the interpretation is the same. Okay. So the KL divergence here in the IID case was between two distributions, one whose mean is equal to mu A, another whose mean is equal to lambda A. Here it is the KL divergence between the rows of the transition probabilities of the MDP. Okay. So the transition probabilities of the MDP, recall, given current state and action, what's the next state? Transition probabilities are of this form. So you take any particular row of this transition matrix, that is a distribution on the state space of the MDP. Now it's a finite state space because of the delay constraint. It's no more a countable state space, it's a finite state MDP. So it's a finite length vector. So you take that finite length vector and the corresponding row between the true instance and the alternative instance, and you do weighted sum of such KL divergences. Okay. That is what the TR star is. It has the exact same interpretation as in the IID setting. In the IID setting, there were only actions. Here, there are states and actions of the MDP. That's all is the takeaway. Okay. And this scale divergence here depends on the powers of the transition matrices of the arms. This is the transition kernel of the MDP, which depends on the transition matrix powers of transition matrices of the arms. The supremum over which the set over which this supremum is computed in the expression for T star, in the IID case, it was just a distribution on the arms. Now it's a distribution on the states and actions of the MDP, which satisfy the flow constraint and the delay constraint, the max delay constraint. So it is very important to capture all these constraints in order to derive a good lower bound. Okay, so that was the hard part in the problem.
So this is like a flow coding.
Yes, the flow, in addition to the flow, there is a
R constraint.
yeah, the R constraint, the delay constraint. Okay. So these are some technicalities. Essentially, it is, if you look at this psi function, which I also showed in the IID setting, that psi function is actually continuous. The continuity of this psi function is easy to show in the IID setting, not so easy in this restless Markov setting, because there are powers of transition matrices which come in these expressions. So in spite of that, that is just saying that we are still able to establish the continuity. Now in the IID case, I showed you a certain mu n star, that is that optimum distribution corresponding to the estimated instance. Here there is a set. We don't know whether this supremum is attained uniquely, whether there is a unique element which attains the supremum. So we allow for a set of sup attaining mu. So W star of theta for any given theta is the collection of all mu which attains the supremum in that expression for TR star. So if you look at the theta to W star of theta mapping, that is upper semi-continuous or upper hemi-continuous, if you want to call it. That is what it is. And here, if you recall in the IID setting, the key idea for achievability was that the empirical proportion of arm selections should converge to the optimum distribution. Here, it's not just arms, it is state action. Empirical state action proportions should converge to the correct set. Okay, this is the most important difference between IID and Markovian settings. So how do we do this? So this is just a formal comparison between what we have versus what Gurrivier and Kaufman had. You see how simple this is. This is a function only of arms. Here the supremum is over all distributions on arms. Whereas here it is states and actions of the MDP. Okay. This is a KL divergence between distributions whose means are theta A and lambda A. Whereas here these are distributions on the state space of the MDP. So you have to take row-wise KL divergence and then weigh them all. So how do we achieve that lower bound? So we use that mixture with uniform idea. When I say uniform, you cannot always select uniformly. Whenever the delay of an arm reaches maximum delay, you have to select that arm. Except that it is uniform. Okay. So under this uniform policy, you can guarantee that the MDP will become ergodic. The DI process MDP will be ergodic. Okay. Uniform policy will put a strictly positive mass on every arm. Very easy to show that it will become ergodic. Now, once it is ergodic, it will have a stationary distribution. Let's call that stationary distribution as mu theta uniform whenever theta is the underlying problem instance. Now, associated with mu theta uniform, you can construct what is called a state action occupancy measure, which is just the product of the stationary distribution followed by the policy. Okay. So here is a conditional distribution of A given DI. Multiplied with the distribution on DI, you will get a joint distribution on DI and A. That for the uniform, I am calling it as mu theta uniform. Okay. So this will be important for us in the policy. So our policy, like similar to the policy by Gurrivier and Kaufman, has one more stage, which is like there are 4 stages. First stage is of course parameter estimation. Okay. We can estimate the mean. From the mean, we go back to the parameter. This is where we use that one-to-one correspondence. Okay. So we estimate the mean. This is just the empirical estimate. Okay. Notice how I have used the function f here in the reward function because the mean is defined as the average value of f. Okay. So this is the empirical estimate of empirical mean, the estimate of the mean of arm A. Invert that and go back to theta. Connect all the thetas and form this vector parameter, theta hat n. Vector theta hat n is an estimate of vector theta, which is the true problem instance. Okay?
This is using the uniform policy, sir. Or policy.
Yeah. I'm going to tell you what I use.
Okay.
But as a first step, at any given time, we estimate the parameter. I'll tell you how I'm going to sample the arms. So we estimate the mean, come to theta vector. Estimated theta vector. Using the estimated theta vector, we will compute W star of theta hat. Remember, W star theta is the set of all new vectors which attains the supremum in the expression for T star. In that expression, replace theta with theta hat n. W star theta hat n is the set of all supremum attaining new. Okay, so we compute this. Then what we do is, you take any element from this, any element. What is that element? That element is a joint distribution on DIA. From that, we have to generate a policy. A policy is an element of the form A given DI. See, if you pick any new from W star of theta hat n, new or new star, let's say new n star is an element of the form new n star of DIA. Okay, for various DIAs. It's a joint distribution on DIA. From this, you should generate a policy which is a conditional distribution of A given DI. You should generate a policy, you should generate a conditional distribution like this. Very simple. You just do new n star of DIA and then you sum it up across A. If you do this, you will get a conditional distribution on A given di. The point is the denominator may not be well defined for every di. So what we do is we mix it with a uniform. Okay. Instead of using this nu n star directly, we mix nu n star with nu theta hat n uniform. Now the uniform part is always strictly positive because one component is 1 by k, which is uniform part. The other part is a stationary distribution which always has a strictly positive mass. Okay. So that mixture and then appropriately normalized. That's all I'm saying. That is the first part. So once we get this, again, I mean, just for the simplicity in the analysis, we do a further mixture with uniform of this. Direct mixture of uniform with this. Okay. So like 2 wrappers of uniform we add into that policy. And how we sample the next arm is according to this 2-layer wrapped phi n. Okay. So this is the policy. And then for this policy, we are able to show that if you set this outer wrapper in a certain way so as to get some nice closed form expressions in some results, we are able to show that the key result for achievability, the empirical state action proportions, converge to this particular set W eta star. So W eta star node will have a convex combination with the eta because the outer wrapper eta is still there. Okay. This is like saying that we have an upper bound of 1 by 1 minus eta into T star. I showed you that upper bound in the IID setting, right? That eta comes because we were mixing it with uniform. We are also mixing with uniform. That's why this extra eta is there. Okay, but that's not of concern. So that was the arm selection rule. Whatever I showed was the arm selection rule. Yeah. How do I stop? So I build this particular test statistic based on the empirical transition kernel of the MDP. So the MDP has a certain transition probability. I don't know the transition probability because it will depend on the theta. So you construct an empirical transition probability for the MDP and use that to construct a certain test statistic. This is actually the GLLR test statistic, generalized likelihood ratio test statistic in the IID setting. This is the analog of that in the Markovian setting. You design a threshold. Remember, I told you that the threshold will have the delta in it. So the delta is the error probability delta which is given to us. You update the Zn and the zeta of n comma delta at the same time for every n. Delta is fixed. You just keep updating it at every n. The moment Zn crosses zeta, stop and declare whatever you think is the best arm as the best arm. What do you think is the best arm? Among the estimated means, the one which has the highest mean is your estimate of the best arm. Just output that as the best arm. You stop and output that as the best arm. That's all. Wait till this statistic exceeds the threshold. Once that happens, at that time, whatever is the estimated best arm, just output that. So we are able to show that that particular policy, which is described here, satisfies a certain, the required error probability delta. Whatever delta you give me, it will satisfy the delta error probability. And it will also satisfy an upper bound like this. Okay. In particular, if you let eta, you can let eta as close to 0 as you want to make the upper bound 1 by TR star equal to the lower bound, which is also 1 by TR star.
So the upper bound is converging in the expectation sense.
Yes.
But the lower bound is
also on the expected stopping time. This was the lower bound. This part was the lower bound.
I see. So you can write this.
Yes. Showing that it satisfies in the expected sense is the hard part. Showing that it satisfies in the almost sure sense is relatively easier. We are able to show that it satisfies in the expected sense also. So the upper and the lower bounds match. That is the lesson. I mean, that's the takeaway. Now, coming to Vincent's question, what happens when we let that R go to infinity? We imposed that R, but really what happens as R goes to infinity? We can show that the problem complexity TR star theta, which appeared in the lower bound on the previous, the lower and upper bounds, the TR star, that will actually increase as R goes to infinity. That means both sides shrink. Okay. Like actually the whole thing, 1 by TR star increases, 1 by TR star decreases. Okay. So TR star is less than or equal to TR plus 1 star because the space is increasing. The more the allowed delay, the closer it is to the infinite state system. Okay. So that's an increasing sequence of positive numbers. It will definitely have a limit. The question is that limit plus infinity or is it equal to this particular quantity, which is actually the problem hardness when there are no delay constraints. So in my whole analysis, if I were to remove that R and compute the lower bound, this is the lower bound. Here, this sum is over a countable state space. Earlier, this sum was over a finite state space based on the R. Now, this is a sum over a countable state space. So the thing is, does that limit equal T star? Is the question. That is, as we let R go to infinity, does the finite system match in performance? Does the performance of the finite system converge to the performance of the infinite state system? So this is still an open problem. Of course, for the IID case, this is true. Every IID process is trivially a Markov chain. So if you let the arms be, if you let the observations of the arms be independent, this is actually true. Because in this case, it's a very, very naive case, because in this, when the observations are IID from each arm, TR star is equal to T star for every R. So the limit is obviously equal. In the restless case, we still don't know. We only know that it is less than or equal to. We don't know whether it is strictly less than or whether it is actually equal. So yeah.
So this T star theta in lower bounds, in the lower bounds, it still holds, right? So
yes.
You can just show that this lower bound holds.
Yes, yes. So that was what I wanted to
know if.
So that's a trivial lower bound.
Yeah.
That is always a trivial lower bound. Whether it can be achieved or not is the question.
You don't know if you can achieve it.
Yeah, exactly. Yeah. This is what we are still struggling with. I don't have a concrete answer for this. But yeah.
So you introduced the R to make the achievability parts easier.
Yes. For any given R, I know this whole boundary is tight. For every R, that boundary is tight. But as we let R go to infinity, are the boundaries still tight? I don't know.
So earlier Kaufman paper strictly considers single
single parameter
exponential.
Yes.
Do you also do that?
I also look at single parameter exponential for Markov chains.
For Markov chains.
Yes. Yes.
If it is not single parameter, then
so the one-to-one correspondence between the mean and the matrix is lost. The lower bound TR star is actually a function of P1, P2 up to Pk.
Yes.
The optimum distribution W star is also a function of P1, P2 up to Pk. We can of course estimate the matrices P1 hat up to Pk hat using some estimation. For example, maximum likelihood estimation or something like that. The problem is maximum likelihood estimates in this case will not have a closed form.
Would it be still a problem in the IID case?
So what would be a problem?
Let's say that it's not Markov chain now. It is the IID case.
Yeah.
And instead of single parameter, you have k parameter exponential.
Yeah. No. Yeah. There it can still be done. Yes. The number of parameters is not the issue. The issue is here. So even if you have a vector parameter, there is something called a mean corresponding to the vector parameter. One can derive in the exponential family, IID case. That mean is still in one-to-one correspondence with the vector parameter.
You may not guarantee
that the analog of that doesn't hold in the Markov case. So this is a very specific way of defining the mean associated with a matrix and guaranteeing that the mean and the matrix, you can go back and forth between the two realms.
And also in your mean definition, so you have inner product with F.
Yes.
Inner product with F and stationary expression.
Correct.
So if you replace and that F matches the
F with which goes into the exponential test.
Yes. Exponential tilts. So if they don't match, so if you replace your F with arbitrary G.
That's also a great question. No, we can't guarantee the one-to-one correspondence.
So if the mean is defined arbitrarily on the.
So all of this is very carefully designed so that we have this bijection. And this is what is the most important thing which is required for the analysis.
If you lose it, so you also use this.
Yeah. We may need to estimate the matrices directly, maybe empirical estimates. But the problem is the empirically estimated matrix may not be ergodic. You may need to mix it with an identity matrix. And you may need to analyze the stationary distribution of that mixed matrix. So it's very complicated actually. I tried all this. Somehow it's very difficult to do the analysis.
Also, how critical is the uniform mixture part? So
It's not about uniform. Any distribution which puts a strictly positive mass on each of the.
why is it needed?
So the thing is, under such a policy which puts a strictly positive mass on every atom.
Force exploration.
Yes. That is the first exploration part. So we are actually going over and above what is actually required. Derivier and Kaufman say a forced exploration at the rate of square root n for time n is sufficient. We are actually going of the order n for time n because we are mixing it with, we are sampling according to a certain probability distribution. So which means we are sampling at the rate of alpha n. Where that alpha depends on the probability that this policy puts.
It's awesome.
Yeah.
That's good. Great.
Yeah, if you have any questions, I'm happy to answer.
So here you don't care about the sampling information.
So there are a lot of things which are, perhaps limitations of this work. One is the computation of this particular quantity. W star, at each time instant, I need to compute this W star of theta hat n. That involves, so computing the W star theta hat n will actually involve solving this particular soup inf optimization at each time step. That is actually a very, very computationally intensive task. In fact, this kind of a soup inf computation has to be done even in the IIT setting. But there some things can be simplified because you can actually simplify this inner objective in the IIT setting. You can simplify it further and you can have some nice closed form expressions for the W star theta. Whereas here, I'm not able to do that. So this is one computationally intensive task. As such, the policy is very computationally intensive, not at all computationally efficient. In spite of the reduction from infinite state space to finite state space, that was the first biggest hurdle. If it is an infinite state space, you cannot even simulate it on a computer.
So did you simulate it?
I mean, it takes a lot of time. I don't have any simulation results in the paper, but even for 3 arms and 2 states, the size of DI space is very huge. With maybe R equal to R. We generally want the R to be more than K for the problem to make sense. Otherwise, you will only be selecting uniform
How
R.
do you complete the soup inf right now? In the
I mean, I just, this particular thing, I just feed it into a solver. That's all. But it takes like too much of time. I don't even know how to simplify this.
Each time
It's very, very computationally intensive. That's the problem. And I need this computation. Because finally, I need to determine what is the distribution according to which I should sample the arms. And unless I sample according to the optimum distribution coming from this expression, I will not be able to show that asymptotic optimality is guaranteed. So to achieve the lower bound, I need to guarantee that I am sampling according to this particular set of distributions. That is, after I compute this, the next step is I will choose an arbitrary element from this, and then I do these numbers. So all of these are very computationally intensive. Yeah, so computational efficiency is bad. There are some papers recently which have started proposing alternatives to Derivier and Kaufman's policy, where there also there is a requirement for solving the soup inf. But now there are papers which have started proposing alternative policies which don't compute that soup inf at each stage and are therefore computationally very efficient. I still need to think about extensions of those policies to the Markovian setting.
And you're also assuming the arms are finite state space markers.
Arms are finite state space.
And
Yes.
if you want to make that
countable or maybe
Yeah, yeah.
Gaussian,
Yeah,
like
yeah.
Gaussian. Yeah, that's also very difficult.
I see.
In the Markovian setting, you will have to then deal with what is called. So here there is something called positive recurrence and all this. When you have uncountable state spaces, you have to deal with Harris recurrence and all
Okay,
that.
okay.
So it requires a new set of tools.
Yeah, also the probability matrix won't.
That's what you'll have to deal with kernels everywhere.
Yeah.
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 It's a very careful bookkeeping of all of that. Okay. There are no further questions. Thank you. Sorry.
So this wrapper का idea